Okay, it should be good.
Not much.
No.
It's good with you. Oh, it's good. Yeah. I know, I go there all the time and my friends are like, you know,
I just wanted to show you a couple of things that I was talking a little bit about. This was one of the meals for Glenn Armstrong, the first person to go into space for the United States. This is what they ate out of here. This is beef with vegetables, ground up, put into this metallized tube, and then sterilized. Okay, and then they had a tube for their space helmet, which they would screw this into and squeeze it into their mouth. And they hated it. Okay? They just hated that. But this package is actually 60 years old, so it's all rusted from the inside out in there. The second round of foods was dehydrated foods. So this is basically Nestle's Quick, and we also had General Foods made Tang for us in there. So a plastic package, on it would be instructions of how much water to put in. So they would cut this, and there was a gun with each click was 1 ounce of water. And then they would have to sit there and knead it. And then they pull off this tube here, put that around the tube on their mouth, and then squeeze that into the tube. Really fun feeding. By the way, there's a little tablet here that if they didn't eat all of it, they would push the tablet into the package itself and mash it up. So that that was basically an antimicrobial, so the researchers could get the food and see how much food they ate or not in there. And then in the Apollo, we went to packages like this. This is sterilized food in it. This was a little further where they could actually squeeze food out into a cup and then eat from the cup itself. It had to be pretty viscous in there. These are retort pouches. The group I worked with at MIT were the first to work on this. The advantage for retort pouch is it's thin. It's about 1/8 the size of a number 2 cannon. And so since the heat transfer is proportional to the thickness squared, you have 8 squared, so 64 times faster in heating this up. And so you got a much better quality product. This eventually became a military food. We call them MREs, meals ready to eat. And the military didn't, they accepted it. The problem was cooking. And so this is a cook package, okay, where you lay the food on this side. You put water into here first, and there's magnesium oxide in here that reacts with the water and produces a lot of heat. And so you can cook the food with this, and the enemies would not see the flames. There's no flames in it. That was one of the key things around this. And there's a few other things here. That retort pouch you can find it in the grocery store. This is tuna fish, but this never caught on in the United States, the retort pouch, for some reason. You go to Japan, in the canned food section, all you see is retort pouches. They accepted it much better than we did. And this is the freeze-dried ice cream there. And you would eat it dry in there. You're not going to mix it up with ice or anything like that. Yeah, so that's the range of different kinds of products. So let me just finish up the last section, which is very important from the standpoint of quality control of foods in industry. There are a number of different devices for doing water content measurement. One of them is NMR, and there's a couple of papers here that go through how you can do this. It's very fast, in seconds. It's good for the range of 5 to about 25% moisture. so you can't go to high moistures in there. The problem is it's not a analytical instrument for the laboratory. Because for each food system and any changes you make in the food system, you have to get a new calibration curve. So you have to make the food to different water contents and then measure that by something else like Carl Fisher. And then you make the curve there that would do this. So this is just showing the moisture content versus what's called 1 over T1. It's one of the spin angles that you get with NMR. And you see a pretty good straight line for that. This is a typical instrument. So you can put it online, aiming down at a bed of food going by, and it would take measurements every 5 or 10 seconds, and then send it to a control unit, would say that, you know, it's getting too wet, we have to go to a higher temperature or slow down, and it was all set up with computers to control the system in there. A very useful type of tool. You can also do this with near infrared. And near infrared, they have machines that are right in the range for various types of products. You can also measure other things like nicotine. It's used in the tobacco industry for drying of the leaves itself. Water has these 5 bands, and it takes about 1 minute per sample. You measure at each one of these wavelengths. And again, it's a very good QA/QC tool. It's the same problem as that. One company, Neotech, has a device that you can get all at the same time, the fat content, moisture content, and the protein content. That's pretty good. Again, you need standard curves for this to be able to use it. I will try to bring it into the next laboratory just to show you. Another way of doing this is to use this device, which we call it a capacitance or resistance device. You've got this tube here, and this is, right now it's down in the down position, but you put it up. It's got a cathode or another cathode that's where you can have a current pass through the cereal that's going to be inside here or the grain, and then back out, and you can measure the water content by, again, a standard curve. So essentially you put the material up here, turn it vertical. There's a trapdoor here. You push this button, the trapdoor opens, the food falls down around this electrode, and then you push the button to put the current through it, and then it reads. And this is an old device. The new ones are digital. And then it gives you a reading for that. And then in the old days, you had to then take the reading and go into a book for each variety of grain. And then it would have a conversion table from the electrode reading to the moisture content of the food. This is one of the more recent devices. It looks very same. The only difference is that it's got a digital system with the background charts. These are the kind of charts that are there electronically. So here's your reading here, and then here's your moisture content for, very specifically, for long grain rough rice. Between these moisture contents that it can work. This is a smaller device that was produced by a company, Protimeter, that I did some work with, and they got an award for this because it was so easy. Other special tests is hydrometers for solutions. Let's say you're buying a 10% sodium chloride solution. Any solute you add to water changes the density of it. It was first done for alcohol, because alcohol has a different density than does water, so the mixture changes in there. And then one for sucrose and one for sodium chloride. These names are the people who figured out to do this. This is the first one that was used for beer and other spirits back in the, just 1800 something or other. I forget the, it's not on here, but it's 1850 something or other. So what you do is you put it into a cylinder, and then you read here. It's got this glass bulb down here that's weighted by lead, and so it will read the a number on this scale, which then you go to a chart, and that will tell you that yes, that's a sodium chloride solution at 10%, or no, it's at 7%. So somebody who sold that to you is cheating on you. So that's, I mean, that was basically what the uses were for. Refractive index is another one. I'll just skip over this. Again, for solutions, you get this is a glycerin water solution. So these are the weight, percent by weight, and this is the refractive index that you measure. It's out to 4 decimals, 1, 2, 3, 4 decimal places in there. It's very, very precise in getting the number for itself. We call them bricks if it's going to be used for sugar water systems. And there's all different kinds of models. They're usually around $300, $400, so it's a pretty cheap device. This company has special ones for different kinds of things. So condensed milk, fruit juices, automatic temperature compensation, juice, coffee, and ketchup, down the line. Very, very quick instrument itself. And then the last one, which is used in the dairy industry, is measuring the freezing point. I have one of these in the lab. Basically, you cool a small sample down to about -6, and then you turn on a vibrator that nucleates the ice forms, so the temperature goes back up, and it then stays at a constant temperature for a while, and that's your freezing point. And it can do freezing point to 4 decimal places. It's got a very special thermistor on it, so you can get it there. Oh, is that the end? Yeah. Yeah.
Is it the end?
Yeah.
Okay.
So now we'll get into water activity. So you see, there's a wide range of things you can use for measuring water content. And with quality control, it means that you've got to set up, every time you make a different kind of sample, you're going to have to get a standard curve made first in there. All right. So if you ever get involved in that at an industrial level, this is a guidebook that we made for doing things in the laboratory from the standpoint of isotherms and stuff. It's about $65, and you can get used copies for about $9 on Amazon. I would do it that way. So we talked about before moisture. This is plotting it versus water activity on the x-axis, on the y-axis, and plotting it on the x-axis. And this question of desorption, we call this hysteresis in there. So that's important, whether you're going to go to the final water content by drying or by picking up moisture. Now this device was basically a device in which a piece of the first ones that were made were hair from women who lived on an island off of Sicily, whose hair was very long, very straight, and what Da Vinci did is he mounted the hair between 2 screws, put a little hook onto it with a weight on it, and as this hair picked up moisture, it would become more elastic. So it would pull this way, and the pointer would go up, and he had a scale of 0 to 100 on it. Da Vinci, he made about 100 of these for various scientists, and for kings wanted to know how humid it was. And so he came up with relative humidity, which in Italian means relative moisture content, but that would be the same as relative vapor pressure. So both are the same. For many, many years, probably over 100 years, the Navy had these devices made. You can see the fiber here. I'll bring one in to the laboratory, so if you want to take a look at it. And it was connected to an ink pen on this side, and this was a round cylinder in which was a 7-day graph, and it would then continuously record the humidity and give you a chart for that. The Navy were the first ones to do temperature and humidity measurements around the world. They were worried about climate change. I don't know, but that was important. And you can make one yourself. Here's the instructions here. I won't read through the instructions, but my children took this to class and had them all make these things. Most of these dial hygrometers, we call this hygrometer. It's different than hydrometer. Hydrometer is the bulb thing that you put into the liquid. In fact, in the old days with cars, we used to have hydrometers that we put into the battery to see if the battery fluid was okay. There was a range that it could be in there. So this is the typical thing. A lot of humidity controllers also use this. And instead of a fiber, they use a ribbon type thing. So it's wider and you get more elasticity and you can get a better reading with that. These devices are exactly that. Very smart idea a German came up with. You take a humidity gauge, which is exposed to air, and you connect it with a pot where you put your sample in, and then you close it and you let it sit for 24 hours, and you read the scale on the front here. It's good between about 0.4 to about 1. So very dry stuff, it's not going to be as good in there, but intermediate moisture it would be. Why don't you pass that down? Nobody steal this, please. Just bring it back. We'll start here and go that way. So in the middle, you pass it on your side. You can open it if you want, but make sure you close it right so it doesn't all fall out. Who has the? So here's a gummy worm. What state is that in? Glass. So what's the water activity? Originally it was about 0.7, but I left it sit out for about a week in the conditions around here. And remember glass, for many materials, glass to rubbery transition is around 0.45 to 0.55. And this is 0.5 in there. So it's right on that thing, which is not too bad. So there is, I forgot to show this, Simon. There's a little screw on the back here. So you can make salt solutions to water activities in the range that you're using, and then you can calibrate the reading to the salt solution. So that's a little bit better than just dealing with the instrument. This is something that inspectors who go to plants where water activity is important, they will bring one of these along. They run about $250, $300, somewhere in that range. So again, a pretty cheap instrument. True equilibrium takes about 18 hours, so it's not something that you're going to get right away in the plant itself. I ran a study with 24 different labs for FDA and a syrup that they had people measure on who were going out, and the value they got was 0.836 plus or minus 0.008, and the range of values that came back from the 24 labs was this, 0.816 and 863. Not that great, not that great. But, you know, the product was held under different conditions, so that could account for that. This is the thing for it. It's the Canadian Food and Drug. They have a manual, and they do have some standard methods using the Lufft meter in there, and it's been archived. This is the value there. So it gives you all the procedures to use. Unfortunately, I can't demonstrate this, but you see two thermometers on here, and they're put on a sling, so I can take, there's a stick behind here, which I hold in my hand, and I can take that and spin it around. One of the bulbs is going to have a shoestring on it, and I looked for some shoestrings in my house this morning, and there weren't any. I have all Velcro shoes or loafers, but the hollow shoestrings, which are hard to find, and you cut off a piece, and you make it wet, and you spin it. Do that. What do you feel? You gotta wet it. Wet it. What do you feel? It's cold. It's cold. What's happening is it's evaporating water on what we call the adiabatic cooling curve, and there's a very specific point where it's going to stop and evaporate the water at that temperature. So the air cools to a certain thing, and the spinning that you do gives you a constant rate of flow of air, and so it gives you a thing. So here's our sling cyclometer. It's based on the properties of air, and I'm not going to go through all these equations in there, but it relates the vapor pressure air times the constant times the mass of the thing. So here is a chart, and I had one that has some color on it so I could show something, but I couldn't find any printer this morning that would print the colors out right in there. So that's a problem. I'm going to try tomorrow in there. So what is a plot of moisture content of air versus temperature of air? Okay. And on that plot, we can draw lines of constant relative humidity. And this is a very complex chart. It's got about 7 different things in there, so it's hard to follow the lines. And one of the lines, which, let's say this was the air dry temperature, which would be the dry bulb, okay? And we go up and draw a straight line in this direction, and then we also look at the temperature, that's the wet bulb temperature, okay? So we go up, this is the temperature, we go up to the 100% relative humidity line, and where this blue line crosses there, that's the wet bulb temperature, where the bulb with the water jacket on it. And then there are lines that come down. They're not exactly that straight. They're curved, but I just put it to look like this. You come down that line, and where it crosses the dry bulb, that point is the humidity of the air. So you're measuring 2 temperatures. You got to have this chart. It can be done electronically, and there are some devices to do that. I'll talk about that. So it's a nice way to measure relative humidity. But, you know, I can't stand over a small jar of food and swing my thermometer because it's not going to work that well for that. It's okay for a warehouse storage bin where, for example, with potatoes, that you're trying to control the humidity so they don't dry out that much. Yeah. There's another thing on this chart. Ooh. Come on. there, oh, it's showing up. Let's go back one. If we took air at this temperature of air and at this humidity, and we put a material in there that we could lower the temperature of that system, you're going to lower the temperature at constant moisture content. So you got a straight line from here, and where it hits the 100% line, that's the dew point. And you see them talk about dew point all the time when they give you weather reports and stuff like that. Essentially, what's happening is at that point, the air in the water becomes saturated at 100% relative humidity because of its cooled down, and it's going to condense on the surface. So you can use dew point as a measure, as well as a wet bulb, dry bulb thing. This is the chart that I use, and I'll get you one with it. So here's that same thing we were showing before, the dry bulb temperature here, and hitting up here on the adiabatic cooling curve, and this was the wet bulb temperature here. And there's lots of other lines. There's enthalpy lines and things like that on it. So it's not that clean in there, but that's used all the time. The key here is to have, if you're going to do it with thermometers, you got to have good thermometers with a lot of spacing along the way. So that you can find thermometers, for example, that have half a degree Fahrenheit. Other ones are up to about 2 degrees Fahrenheit, you know, as measured on it. And this just shows you that, and unfortunately this got moved over, that with a 2 degree Fahrenheit on your reading would be somewhere between 46 to 93% relative humidity. Useless. Useless. If you go to half a degree, it's going to be between 61 and 73. So not very good in there. So we really can't use these that well for measuring of foods itself. So the errors are accuracy of the thermometer, the wick getting dirty. Most of the micro labs where we have those walk-in coolers, they're supposed to have controlled humidity to keep it up, so the agar plates that you put in there are not going to dry out. And unfortunately, nobody has cleaned those wicks in there, and there's no water in the jar that the thermometer, the thermocouple goes into the water, you know, with a wick on it. And so that's a real problem on there. But it is used in large storage sheds. And here's getting around the problem of an electronic device that has all the calculations in it, so you can get pretty good numbers on that. And here's the probe here. You can make this probe fit inside a jar and then put food in that jar and then measure the water activity that way. And this is another one. They call it a digital sling, and that's what this is called, I should say. This is called the sling psychrometer. That with the two temperature measurements. If you can't afford instruments, many Asian countries and African countries, so there's other simple ways of doing this. One is to put, guess around where the food water activity is and put it in desiccators so it picks up moisture to a given water activity. In this side it's losing, this side it's gaining, and then draw straight lines, and then somewhere in between is the true water activity. Not a very accurate thing, but it's good enough for some uses. One of my graduate students came up with a procedure which I thought was very good. We made isotherms for a very, very stable product called microcrystalline cellulose. It gives a nice type 2 isotherm, which we'll see. And what you do is you put 100 grams of food in a small desiccator. So that's the salt solution, is the food. And you put 2 cups with 1.6 grams each of microcrystalline cellulose. wait for 48 hours so that it equilibrates, and then you measure the water pickup by weight of the two samples in there, and then you go to your standard curve isotherm, and you can read the water activity off of that. So it's a neat little approach. There's the Australian Food Research. They use a glycerol in a jar, just like the previous one, but and then they measure the refractive index of the glycerol in there. So that's a very similar type of thing as the FET force, and I'm not going to go to that. So, what we wanted to do is get away from all these types of things, and can we do something similar to Vinci, but measure the electrical property of change in the fiber? So we have a fiber, we maybe mix some salts onto that fiber to give it a certain range that it's going to work in, and instead of looking at the elasticity of it, we can pass a AC or DC current through the fiber, and then get a standard curve for this, and we can then get the water activity of the product. So a particular one is lithium chloride in a nylon fiber wound around a thing, so you get a lot of exposure area, and you put a current through it, and that can give you this, and this is the range for that lithium chloride. You see it's very steep, so a small change in relative humidity is a steep change, so you got a lot of power in reading the water activity that way. This is it here. There's 3 pillars in there where there's continuous winding of this lithium chloride, and we designed this with a little jar, and the 2 things hooked out here that went to the instrument. This was the first electronic instrument I had. It cost about $20,000 because nobody else was making instruments at that time that could do this. This is a polysulfonated fiber, and you see here it's fairly steep, but when you get out here, the change in measured resistance is much smaller as a function of relative humidity, so you get less sensitivity for it. So there are different elements like this. This was the first really good instrument that came out, Rotronics. This is the cell that you put your sample in, and this is where the measurement system is in here, and you could actually measure 2 there because you could attach another one on the back and have 2 at a time going on the instrument. Same thing itself. Most physical chemists started using the Rotronics. It was a US-based company, and this was a nice one that had a lot of mahogany and stainless steel on it, and this was what the microbiologists bought. So there was a big battle, which one is the better, and they're both basically the same. They use the same sensor in them, in there. And in those, in the 60s, 70s, they cost about $15,000. Now they're about $25,000. But they're okay. They're a good instrument for measuring this. And again, the Canadians have put together a procedure to do that. The limitation is time to equilibrium. In both of the booklets for these instruments, they say it's in equilibrium at 1 hour, and it actually may be up to 18 hours. That's one of the critical issues of the instrument. You want to make sure you have a large sample to air volume inside the thing so that you can have it equilibrate pretty well. And I think it's good to plus or minus 0.01 itself. But you need to standardize it, the reading in there. And they set the reading as water activity, but that can change with time because these fibers can pick up other volatile materials and start changing the properties of it. And that's one of the bad things of it. So you really should, if you're doing research, you need to do a standard. And then test tests 3 standards monthly to see if it's drifting or not. And if it is, there's ways for the instruments to be recalibrated, just like the other instrument I showed you there. This is a neat little one. This is a similar type instrument, but designed to be very small. The sample cup is here. This is the only thing I don't like about it. It's hard to do it. If you do it that way, you're going to drop all your food out of it. But there's the element that's measuring it there. It's essentially connected to the fiber system. So this is we call this an impedance type of device. You put the sample in, close it, and in about 10 minutes you got an equilibrium value in there, because such a small space in there that it calibrates very rapidly. $3,000 for something like this. I've had 2 of them stolen from my lab. So don't do that, please. You can do phosphorus pentoxide as a sensor. It's very good for very low humidity air. In certain industries, you want to have humidities less than 10%, and it's hard to measure. So this is more sensitive across that. And these are very expensive, about $30,000 for something like that in there. AOAC has a section on water activity measurement in the processed vegetable, canned vegetables, because of the regulation of the need for 12 Watt cycles killed if the water activity is greater than 0.86, like that, if you're going to make it into a shelf-stable product. Unfortunately, this is useless because only for Rotronic in here, that's the only one still being made. Most of these other instrument makers went out of business. They just didn't do it very good. And this is the standardization. You want a sample that's about 95% of the total volume, 5 salts for a calibration curve, record time, AW versus time in 15-minute intervals, and report to plus or minus 0.01 in there. And what basically they said is equilibrium occurs when 2 readings are less than 0.01 difference in there. So very simple. And that's referred to in 21 CFR 113, which is the canning, low acid canned food regulation. The best instrument around is the dew point device. And did you guys measure water activity yet or not? Mm-hmm. Yeah. That's the Decagon device. That uses dew point. Very simple. Your sample is in this chamber. In this chamber is a mirror slide, so it's a shiny mirror surface connected to a Peltier device. Peltier device is a way of using 2 metals together that if you pass a current through them, you can, depending on the current that you pass, you can cool the sample down. So it's an electric refrigerator without a compressor, noise and stuff like that. They were first designed, and the work was done at MIT by a friend of mine. It was first designed there basically for all the motors that were small enough that we could do it by where you needed temperature control. You can do it with a Peltier device, so you were able to get a submarine that could run deep, run quiet, run silent, because you don't have all these compressors going. Especially a nuclear submarine, you don't have the compressors, and so that doesn't make noise. So what happens is that mirror has above it a light bulb, and nowadays they use a laser, that shines onto the surface. And this surface cools very, very slowly, and at some point the surface is going to be cold enough that dew will form. And that will change the intensity of the reflection to this sensor over here, which is sensing the intensity of the light coming up. And so it looks at when that all of a sudden goes down, and that would be the dew point. Because you know the temperature from the Peltier device, and then it's got the mathematics in it to take that psychrometric chart and put it into equations, which is a lot of pretty big memory for something like that. I work with a company in England, Protimeter, that made a device like this, but they came up with an interesting idea to get a better number, is that once it hit the first time it hit the change, it wouldn't just accept that, it would then raise the temperature, so the water would evaporate and then cool it, but only go about 1 or 2 degrees above the dew point, and then come back down again even slower, and it could get a better measurement of the dew point in that. So, where else do we see this phenomenon, dew point? You ever get frost on your car? Right? That's called the frost point, because once you get below 32, it doesn't form water droplets, it forms ice on it. So you go from the vapor state into the frozen state. What time? We go? 5 more minutes?
Yeah.
Okay, that's what I thought. If you have a windy day, you're going to get dew formation overnight? No. Someone said no? Well, if you have wind, you've got now convective heating of the surface, and so it doesn't cool. On a clear night, when the temperature is going down slowly, okay, if you remember maybe you haven't had it yet in physics, the air is going to, the surface is going to cool down because it's radiating heat into space. And space is close to absolute zero, minus 273 degrees centigrade. And so that's what's cooling the surface. And it's cooling very slowly. So it's like the other device, the dew point device I showed you. Water will condense. If it's going to be below the freezing point, then water will freeze onto the surface. So if you have wind blowing, or if you have clouds, you don't have the radiation because it's not absolute zero. It's the temperature of the clouds, the lower part, and that's pretty warm. Heat transfer by irradiation is a function of temperature of your surface to the 4th power in Kelvin, minus temperature of the space to the 4th power. And if it's zero, there's a big difference there. So that's why it's going to form that dew on the surface. So this is what we saw before. We measure the dew point at a given dew temperature. We go up to the 100% relative humidity line and draw a straight line across to where the air line for the actual temperature of the air. And so this is surface temperature, this is air temperature, and then where it crosses here is the humidity of the system. And that's the Decagon device there. Again, that's just showing it. And there, I'll try to get you one of these printed out. If it's black and white, you can't really discern what this is trying to show itself. Limitations is dust and volatiles condensing on the mirror. So with intermediate moisture foods that have polyols, like glycerol or propylene glycol added, those can evaporate as well and condense, and that can screw up the reading. Low sensitivity at very low vapor pressures. You need a clean surface, and you can dry out the food because that's where the moisture is coming from. And if it's low moisture food, then it makes it even more difficult itself. But here's a typical standard curve, R square of 999 if it's working right. So that's the measured water activity on the instrument versus the literature water activity on the x-axis for the various salt solutions. And then we'll talk a little bit about isotherm making. This is a very expensive instrument, about $150,000 to $200,000. It basically has, in this chamber here, it has a glass spring, or it can have a tension wire that's metallized, and it's got a little sample cup that you put the thing in, and you can program now the instrument in steps, let's say every 5% relative humidity, and waiting for maybe 5 hours between each step, or lesser time. So, and you can get the isotherm from that, or you can measure the water activity if you have a standard curve. This is not an instrument that people are going to buy to measure water activity in a food company. The Decagon has made a benchtop device that costs $40,000. Unusual architecture of this. What does it remind you of? Ever been to Cuba? No? Lots of cars built, U.S. cars built in the 50s. And they had very, very blatant types of colors and rounded corners and surfaces. And the guy who built this device, the engineer, he purposely did that to look like an automobile in there. And their new one is a little bit better looking. And basically you put a sample in here, it forces water at increasing relative humidities through, and then it measures the weight because the sample cup is sitting here on a weighing dish type of thing. And so you can get a water activity versus moisture content curve over the thing. And I think I'll stop here because I've gone too far. Right?
You're welcome. Yeah, pretty cool.
Can somebody bring the cups back up?
I remember. Thank you.